Okay, so our next speaker is Professor Daniel Loss, and Professor Loss, you are on. Thank you.
Okay, can you hear me?
Yes, loud and clear. And we can see your slides.
Okay, good. So I can start.
Yes.
Okay, good. So thank you very much for the invitation to give a talk here. I have to say I regret that I'm not there in person, but it was just not possible due to other constraints. But anyway, so here I would like to present some results and some insight on spin qubits, and I will focus on spin qubits in semiconducting systems, and in particular for holes in quantum dots. And I should also acknowledge, to begin with, collaborators on this project. They are listed here. I hope you can see my cursor, in particular Stefano Bosco, postdoc in my group, and also Peter Stano in Riken. And on this side here, my experimental colleagues with whom we have collaborated. And down here, the acknowledgements for funding. So let me see, doesn't work. Yeah, I should actually say that we just finished last week a conference, the biggest conference on spin qubits. This is spin qubit 5. I just want to flash this quickly so that you can actually see how active the field is. Here on the right hand side, you see all the participants. It took place in Switzerland, in Pontresina, in the mountains. You can read up here on the web page link, which is indicated here. And you can see it was a full program for 5 days with all the names of players worldwide in the field giving talks here in person. But anyway, this is just to show that there's a large activity in the field. So the outline of my talk is that first I give a brief overview on spin qubits, and then go more into the specific type of qubit, namely based on holes instead of electrons in germanium, and silicon structures, nanowires, and other related structures. And we'll say a little bit some recent results so that you can actually see what the active boundaries of research on hyperfine interaction for hole spins, and mention some sweet spots analysis. And if time permits, I will also say some words about recent results on strong, ultra-strong spin photon coupling for hole spin qubits. So here down, there are some references on reviews, recent reviews. So as you probably all know, there are a few front runners for building quantum computers. So my subject here is spin qubits in semiconductors, but there are also other ones. You've just heard the talk by Professor Tsai on superconducting devices. There was a trapped ions. I guess you will hear more about this in this week, and perhaps also topological quantum computing. One very brief characterization of these systems is a little bit of a bias that the spin qubits in semiconductors, they are really small. And they're also fast in the sense that in principle they have clock speeds like transistors in our current computers in the range up to gigahertz, and sizes tens of nanometers. The other devices and platforms, they are much more advanced. For example, for superconducting devices, they're more than 100 qubits, I think, available by now by IBM, and I think also Google. But one can say a little downside there is that they are rather big, hundreds of micrometer in scale, and also not as fast. And topological quantum computing is an exotic idea, which is based on Majoranas, but Majoranas recently also had some setback, and I think it's still an open question whether Majoranas actually do exist in solid-state systems. Here, just indicating there are many industry labs also involved worldwide. I will not just mention all of them, but you can see that this is a very growing area. Coming back to silicon and spin qubits, just this year in the Nature issue in the beginning of the year, there was one issue where we had 3 papers on silicon spin qubits. I should just mention briefly the groups in Riken by Sego Tarucha's group at SEMS, where they showed universal quantum gates about fault tolerance threshold in silicon. And then another very important paper from Lieven van der Sijpen group from Delft in the Netherlands, where they also demonstrated crossing the surface code threshold. And then from Sydney, UNSW, by the group of Andrea Marella and Andrew Jurak, where they also had very high precision tomography of 3-qubit donor processor in silicon. As we go on, I will show more experimental kind of achievements in the talk. So there are many candidates in, I should push this here. There are many candidate materials for spin qubits coming from the first proposal, which we had, I guess now 24, 25 years ago, shown here by this sketch on the right upper hand here. And materials can be gallium arsenide semiconductors, indium arsenide, and so forth, as is written here. They can come in different geometries and confinement. They can come gate-confined quantum dots or self-assembled quantum dots. They can be in nanowires, elongated structures. They can come as electrons, but also as holes in systems. And in the 4 class of semiconductors, there we have carbon. They can come as nanotubes or in graphene, diamond, silicon carbide, or donors, phosphorus atoms in silicon, where the nuclear spin is the qubit. And most importantly, silicon and silicon germanium quantum dots or nanowire structures or transistor-like structures, so-called FINFETs. Another area where also spin qubits are studied are molecular magnets. Now, this is at the more atomistic level. For example, copper rings or cobalt and so forth are candidates people investigate heavily. For this material, the 4 semiconductors, a typical band structure is shown here on the right-hand side of my slide. And here, this is a typical conduction band. Oops. And this here, valence band. So electrons are in the conduction band with a positive mass and valence band with a negative mass down here. I will say more about this in the following. So here, a very simple question. When is a qubit a qubit? There are many 2-level systems, which are bits, classical 2-level systems, up and down. And we call it basically a qubit if we can form a coherent superposition of a 2-level system. So as it is indicated here in this drawing. And in quantum mechanics, this decoherence or the coherence will not be maintained for too long, because coupling to other degrees of freedom in the environment, and we have a decay. This decay time, the decoherence time, defines basically the quality of a qubit. And we would like to have that this decoherence time, called T2, as shown here, is about 1,000 times longer than the gate switching time to change the state of a single qubit, as indicated here, for example, to switch a spin from up to down. And we would like to be able to have 1,000 such operations before the coherence is lost. There are many types of coherence. One should also say it's not only purely exponential decay, like indicated in this curve here. In very cases, it is a Gaussian decay. The time scales are not much different here, or the names, let's say. And there can also be power law decays. There is quite a long history of such measurements of T2 times, as indicated here as a Gaussian decay. And here is a table over the times of spin qubits in various materials, again here in 3-5 semiconductors, the green dots, or in germanium, silicon, purified silicon without any nuclear spins, and phosphorus donors and carbon nanotubes, and the various times one can measure here. T2 star, this is just the unfiltered time, and then echo measurements can be performed, the Hahn echo T2 Hahn, or dynamically purified time scales, or driven Rabi time scales. And you can see as a function of time, these time scales actually increase more and more, and they are now in the range, can go up to milliseconds. Phosphorus donors even can reach almost seconds of coherence times. So here again, a few of these time scales here of the different types of qubits which can be formed, hybrid qubits, spin 1/2 qubits, single triplet qubits, and so forth. And this year, what is also very important is to compare them with the time it takes to perform an operation. So operation times are indicated here. So, and then also the readout of the measurement is an important time scale. You can read more about this in this work, which just came out in Nature Review Physics, where all these tables are listed. Here, I just would like to mention that also the holes have very interesting time scales now, and they are in the approaching T2 star microseconds or so, and purified hundreds of microseconds. The nature of holes and that they are suitable for spin qubits has been pointed out also many years ago, and shown that it's possible to use them for quantum computing purposes. In recent years, the material of choice, shown in this slide here, is germanium, has become very important besides silicon, and I will say now a little bit more about this type of material. So here are different structures of germanium. Here's just bulk, which has a band structure indicated down here. And as I said, there are two important bands, so-called heavy hole bands and light hole bands. The curvature defines the mass, and the more curved it is, the lighter is the mass of the particle, hence the name of this. The valence bands are not just only missing, or the holes are not just only missing electrons, but they also have a different Bloch wave function, which adds then complications coming from spin-orbit interaction. In the beginning, that is considered to be a problem, spin-orbit, but we understood now in the course of time that the spin-orbit is extremely useful to control actually a spin qubit electrically very efficiently. Confining germanium, for example, into heterostructures indicated here can lead into additional splittings of bands and rearrange the band structures. Also, if they are kind of wire or hot wire structures, we get different bands and so forth. And if there's a core shell rolled up structure with a core of germanium and a shell of silicon, we get another fine splitting of the band structure. So this shows that the holes are very strong, dependent on the geometry, and the holes are also tunable because of spin-orbit interaction in them. I will not go into the details largely of the of hole physics, because it's rather complicated, and I just want to illustrate this here by the complexity of the Hamiltonian. So the simplest model Hamiltonian for the valence band is the Luttinger cone Hamiltonian. It's already very old. It's from the 50s, but still applies very well to the systems, and is written down here. So it has a kinetic part, and then it has a coupling between the momentum of the holes and the total angular momentum operator, which is a angular momentum which consists of the spin angular momentum and the orbital angular momentum, which is picked up by the Bloch wave function. And there are then additional terms which lead then to heavy hole, light hole bending, and the split of bands are not included here. So writing out this Hamiltonian is a 4x4 Hamiltonian as written here. The upper corner, lower corner here describe the so-called as I said, heavy holes with a spin plus 3/2 and minus 3/2, and the inner core here are the light holes with plus and minus 1/2 JZ quantum number. In addition, one needs to take into account strain in this material, given here by the Beer-Pickus Hamiltonian, with the strain tensors epsilons, not going into much detail. And we also have to add here confinement potential, electric field effects, and magnetic terms which couple then to the effective magnetic moment of the holes. So even if in the end the qubit is only a two-level system, it's rather complicated, and there are many, many possibilities to squeeze this out of this object here in the low energy sector. So there are many, many parameters to understand for the control of hole spin qubits, such as strain, electromagnetic fields, growth direction, confinement potential, and so forth. So this, on one hand, is rather demanding. On the other hand, this leads then to highly tunable qubits. And for this, you also need effective models to get in, to gain insight. So here is one of the first experiments a few years back, which just used off-the-shell kind of semiconductor material, silicon, which is a structure used, for example, in transistors in your iPhone or in computer. And the Grenoble group in France managed to get this system into a qubit behavior. And this was a very important breakthrough in the field because this showed that it's possible to use existing structures or modify them slightly to get spin qubits out of them. So here some coherent oscillations shown, reached at that time with Rabi oscillations at the frequency range of 85 megahertz and T2 start times between 60 and 200 nanoseconds. In these structures, it's not so easy to confine the holes, so they were able to confine about 10 holes per dot. Ideally, one would like to have one, and this has then been achieved later. So here is another set of experiments done by the Zumbühl group in Basel, my home institution, where a nanowire core shell, nanowire, germanium silicon core shell nanowire was gated and shown to behave as a quantum dot and show coherent oscillations, confinement, as you can see here in these plots, and that they have very strong spin-orbit interaction, which one can read off from the spin-orbit splitting induced of levels in the quantum dot, and a spin-orbit strength was deduced, which is very large, several milli-electron moles, or expressed in lengths on the order of 50 nanometers or so. And this is the distance one has to travel inside, let's say, a nanowire to flip an hyperfine, to flip a hole spin from up to down due to the spin-orbit interaction. That's a rather strong spin-orbit field. It was also in a planar structure. I show here some recent experiment from the Veldhorst group in the Netherlands, where they managed to confine 4 quantum dots, gate them, and get 4 hole spin qubits. You can see here the 4 qubits show all coherent oscillations, and they were able to empty the dots really down to low filling 0 or 1. It was also possible to get very high single gate fidelities, more than 99%, switching times on the scale of 100 nanoseconds and so forth, and coherence times several hundred nanoseconds with CPMG. So that means dynamical purifying the coherence. It was possible to push this up to hundreds of microseconds. So this kind of experiments then established definitely that the spin coherence of holes and electrons are about the same as predicted in earlier theories. Here's another recent experiment from the IBM and Basel group, where they showed that in a silicon FinFET, so it's a type of fin carved out in silicon, and then by gates, it's kind of a nanowire. Quantum dots can be defined as shown here, and they were able to confine 2 quantum dots and show that they have very nice coherent properties and can be driven coherently even at elevated temperature exceeding more than 4 Kelvin. This is also a very important breakthrough, because this means it's no longer necessary for these type of experiments to use cryogenic temperature cryostats, which simplifies enormously from an experimental point of view the control of the system. Also, spin orbit in these structures turns out to be very strong, with the lengths on the order of 50 nanometers. Yeah, here again, similar results on the temperature dependence, that basically coherence is maintained up to 4 Kelvin or so. So in this plot here, there is echo technique used to prolong the coherence time from 440 nanoseconds up to about 6 microseconds. And from this analysis, one can deduce that the coherence is limited, or this T2 star is coming from nuclear spins in silicon, which agrees well with theoretical estimates. So it's at this point rather hyperfine, not charge noise. I will come to this later in my talk. Then I should also say that if there's charge noise, which after, for example, purifying the systems, purifying means removing sources of coherence like nuclear spins, then charge noise will be very important. But it has also been predicted that in these structures for holes, the charge noise can be reduced at the sweet spots. And the sweet spots, they depend on the growth direction, on the direction of the magnetic field and electric field. So here is a theory calculation done by Peter Stano in Riken, basically showing that if you change, or if you orient the magnetic field in a preferred direction, which is measured by this angle phi, that the coherence time can be strongly increased by applying an electric field perpendicular in this direction, confining the wave functions, and the confinement of the wave functions can then basically change the nature of a mixed heavy hole, light hole, hole spin, let's say in a purely heavy hole, and then time can rather much increase as indicated here. In order to see this, one also needs then to go even beyond this model I showed before, the Luttinger model. So these calculations are extremely demanding. It took several years actually to make this kind of calculations. And very recently, an experiment by the Grenoble group confirmed this theory prediction and showed that indeed, as a function of the electric field, as shown here, the T2 time could be increased by almost a factor of 10 by changing the orientation of the electric field and also the strength. So this is all very exciting developments, and we think actually the sweet spots can be further improved in this type of setup. So now a little bit more on coherence times and the remaining sources coming from the nuclear spin. So the hyperfine noise still limits the coherence times, as I said, on the order of 400 nanosecond. And there are two strategies. One is isotopic purification, which just reduces the number of nuclear spins. This, however, is a rather expensive procedure. And now as the geopolitical situation has turned out actually to be very, very demanding. But is it really needed? And this is a question which we asked ourselves just recently, and could actually show that there are situations where sweet spots exist even for the nuclear spins. Why is this so? Here, very briefly, for electron spins, if you have a quantum dot with a confined electron, so it's described by this envelope wave function here, the Bloch wave function at the site of the atoms, the black dot, is an S-wave nature, so the wave function there is qualitatively largest. This is quite different for holes, which are P-wave natures, where at the nuclear site, the overlap of the hole or the electron with the nuclear spin is zero, so there's no contact hyperfine interaction possible for holes. On the other hand, there is some interaction left, which is a dipole interaction between the magnetic moment of the electron spin and the nuclear spin. But this interaction typically is highly anisotropic. We also understand now in more detail what the hyperfine interaction strengths are, as listed here. So for silicon, they're much smaller than in germanium or in gallium arsenide, but still they are quite important. So one can show that hyperfine interaction is describable in the envelope function approximation, as is shown here. And for holes, this has a very important aspect, namely that for heavy holes, which are described in this matrix here by the red entries, there is no direct coupling. And only for the Z component, there is a coupling to the hyperfine spin and the nuclear spin. And that means that for heavy holes, the coupling is purely icing. Whereas for light holes, all components contribute, and it's an isotropic hyperfine interaction. And this opens now a strategy to deal with the noise coming from nuclear spins. Namely, one can try to tune the heavy hole, light hole mixing. So how much content one can give from this to this, vice versa. And this will allow us then to tune the hyperfine interactions. I have a quick question. How much time do I actually have available?
Actually, in total, you have 9 minutes more, but
9 minutes more.
Yeah, but immediately after this is the coffee break. So I'm not strict on time now.
Sorry, I can hardly hear you.
Immediately after this is the coffee break.
Okay, good. Yeah, good. 5 minutes. Yeah. Mm-hmm. Okay, so I will not go into more detail, just to say that one can calculate now the contributions of hyperfine interaction in the low energy sector. An important fact is that the direction of the magnetic field matters. So the hyperfine field of many nuclear spins forms an Overhauser field, as is indicated here, just adding up the nuclear spins. Gives an effective field seen by the electrons or by the holes. And this field has a Gaussian distribution. Now, if the direction of the applied magnetic field is along this hyperfine field, then we have, a Gaussian decay, which is fast. Whereas if it's perpendicular, we have a slow decay, it's power law decay. And this basically means that the fluctuations transverse of the nuclear field will not be seen if you have pure icing type of interaction, as I said before, is the case for heavy holes. So this can now be exploited, And here is the result of this, quickly shown that this decay time of a hole due to nuclear spins can be highly controlled by electric fields. So it increases here at these sweet spots. This is an electric field applied, let's say, perpendicular to the structure. Here we have the quantum dot. And I apply electric field. Let's say this is in silicon. By confining, I basically separate heavy hole from light holes, and I get a purely heavy hole type for the spin qubit, and that decouples it from the nuclear spins and makes it very long-lived. The upshot of this is that at this sweet spot, the coherence time can be prolonged by a factor of 10 or so, and this is about the same as when we gain from isotopic purification. So it's a very useful thing just by arrangement of fields and structures to get a large increase of coherence by applying the direction of the magnetic field properly. Very similar for other structures in silicon in FinFETs, and there it even coincides with sweet spots of charge noise. In the interest of time, I will not say much more to this. This is these are results which you can read up in this recent PRL here. So this leads me to the summary of kind of the first part of my talk, where I talked about whole spin qubits and the hyperfine interaction, and shown some state-of-the-art experiments. If there are a few minutes left, I could say just a few words about recent results on very strong spin-photon coupling, which also has been very interesting avenue now in this field. So in order to have a scalable architecture, there have been proposals made that one can put systems into clusters of qubits, which are then connected by quantum links, and such a quantum link could be provided by photons, for example. So here is a setup with strip lamps, for example, superconducting strip lines where spin qubits could be coupled. In these particular structures, germanium and in silicon, it turns out that there's an exceptionally large spin photon coupling possible, which leads into the strong coupling regime. So the coupling strength effectively can be on the order of a few hundred megahertz. There's a Hamiltonian of the photon field in the cavity coupled to the spin. And if you have a longitudinal control, which is possible in these systems due to spin-orbit interaction, we get a exceptionally strong coupling of this order. And here on this plot, again, it's shown that this can be very efficiently tuned by the electric field applied to these structures in one of the directions. One can use this also for coupling two qubits. So for example, here is an experimental result done for electrons by the group in Princeton, by Jason Petter's group at UCLA, where they showed how to couple single qubits to strip lines. And according to our theory, it's possible to have two qubits very strongly coupled and ending up with an Ising interaction between two qubits in such a strip line, which is rather strong. Can reach gating times on the order of tens of nanoseconds with very high fidelity in silicon or in germanium. So these are still predictions, and we hope that in the near future, this actually will be implemented in the experiment. Good. So this leads me to the end of my talk. Sorry, I went a little bit over time, and thank you for your attention.
Thank you very much, Prof. So we'll take questions now. Now there's a question in the chat from Sonia. What's the origin of strain in the whole spin control bit Hamiltonian?
Yes, this is a very good question. So the origin of strain is just coming from the mismatch of the lattice constant of two materials. So let's say in the structure which I showed, get this away here. Go back. This heterostructure material over here. I try to remove this. Can you see my slide? I have some problems here.
Yes, we can.
Yeah. Okay. So in this structure, there are two materials coming together, let's say silicon and germanium, and they have different lattice constants. And when they match, there will be a stretch or a compression. And this will then cause strain, and this strain will be relaxed as you go away from the interface. And that will have an effect in the end, which is similar to a spin-orbit interaction. And then this can then affect the strength of the spin-orbit interaction and the coherence properties of the system. It can introduce also charge noise if it's local, and if there are, let's say, the tangling bonds, which will affect then the effective splitting of the qubits. Strain can also be induced just by the gates, the metallic gates, which are on the surface of the material, also because there is mismatch of lattice constants of the metal with the semiconductor. And so strain, in the end, is a very important aspect, which helps actually then to kind of optimize the performance of qubits. But it's also very difficult to understand in detail, because not all device structures are known in such great detail that we know exactly in which direction the strain and what non-uniformity the strain has.
Yep. Thank you very much. The next question is from Bernard. So he's asking, what is the particularity of Hall spin quantum dots?
The particularity, maybe I'm not sure what you mean by this. You mean what is special about Hall spin qubit? Yeah. Okay, so in contrast to electrons, holes have a richer structure connected to the underlying atomistic structure of the material. So as I pointed out, the holes consist of p-wave Bloch wave functions, and these p-wave Bloch wave functions are not spherically symmetric. They are anisotropic, and it's these states which can actually see the atomistic spin-orbit interaction. So there's a relativistic spin-orbit interaction which we get if we go beyond the Schrödinger equation. If we look at the Dirac equation, then the momentum of the electron and its spin are coupled. And it's this type of spin-orbit interaction, the relativistic correction, which gets very, very much enhanced in a solid state environment through the lattice structure, because there are atomistic potentials very close to each other, and the electrons have to go through that. And there the effective spin-orbit interaction can be amplified by a factor of 1,000,000 or so, such that the tiny correction which comes from the relativistic spin-orbit interaction in free space has a very substantial contribution. And holes see then this spin-orbit interaction directly in their basis states in such a way that there is no separation between the orbital part of the electron and the spin part. They are very strongly intermixed. A great advantage of this is that we can then control the effective spin via the orbital degrees of freedom. That means via the charge, that means via the electric field. So if we apply an electric field, then this more or less acts directly then also on the spin. And this is not the case for electrons. So for electrons, it's much more difficult to control them directly by electric fields. In particular, I mean the spin of the electron. So in most of the experimental setups, in order to control the spin of a pure electron, one applies then, for example, electric field gradients by micromagnets and shakes the electron in there. Adding micromagnets to a semiconductor adds complexity in the structure and potentially also noise sources. And this is not the case for holes, because the spin orbit is directly built in the ground state, and we don't need then to add additional micromagnets.
Thank you very much, Prof. Any other questions from the audience here in Kigali? Okay. So there are no other questions. So Prof, we'll be grateful if you could send us your slides.
Okay, good, yeah.
So you could send it to us at either to me or to Franco. So we'll be happy to receive it. Thank you very much.